All right, so your midterm exam is May 6th at 6 o'clock, all right?
Wait,
and
6 a.m. p.m. Oh.
6 a.m. 6 p.m. 6 p.m. to 8 p.m. I'm gonna tell you the room. I gotta talk with Miss Marsha again and get you. She's trying to get the room together. Okay? It's May 6th at 6 p.m. All right, and I'm gonna let you know where. All right. So yeah, and so we're gonna have one more exam on 4, 5, and 6. That's your next exam. It's gonna come up before the final. So one more exam and the final. And the final is comprehensive, right? 1 through 6. All right. So today we're just gonna go ahead and move forward through so we can finish up 6, and then next week, I don't know exactly what day your exam is. I know it's not gonna be Monday, right? So we're gonna start reviewing for your 4, 5, and 6 exam next week. So it's not gonna be Monday. It might be like Friday, but I'm gonna find out for sure. Okay? But I know it's not gonna be Monday. All right? But we're gonna review on Monday, 4, 5, and 6.
I have a question.
Yes.
If we're not going to be here on Monday, on Friday, when can we take it?
Say it again.
I'm not going to be here on Friday. When can we take it?
When can you take what?
The 4, 5, and 6.
If you take it on Friday.
Yeah, if it's on Friday.
I didn't say. I said. You talking about this? You talking about next Friday?
Next Friday.
Well, you gotta take it the following week, I guess. Or you gonna have to arrange with me when you know, whenever. I don't know when can you take it. You tell me. It's up to you.
Okay.
Yeah. I mean, I don't know how you deal with all your other faculty, but it's on you. You tell me when you gonna take it, cause you gotta miss the class, right?
Mm-hmm.
So you tell me. And so for those of you who have not taken the midterm, after today, you're SOL. After today, don't even talk to me about it no more. After today. So if you didn't take it and you forgot that you didn't take it and you figure it out on Monday, you're SOL. All right? So, and if you didn't take the first exam, yeah, you got to eat that. Because I gave the results back already. So you got to eat that. So that's why today is the last day for the midterm, because I'm going to get the results back soon. Yes, sir.
You said May 6th, right?
Yeah, I said I don't know where yet. I'm going to tell you. Is that what you just asked me, where?
No, not where. I was just saying, this is for sure May 6th.
Oh, yeah. The university said that. Yes. Yeah. May 6th. And was it 6? Yeah, 6 o'clock. p.m. All right? All right. So let's go ahead and wrap this chapter 6 up so we can start reviewing. Okay? Well, next week we're going to start reviewing. All right, so chapter 6 is on thermal energy and thermodynamics, right? And so, thermodynamics is, if you break the word down, right, it's how heat changes, right? Dynamics of heat flow, okay? And so we're going to talk about temperature, obviously, absolute zero, heat, right? Quantity of heat. We'll talk about some laws of thermodynamics, entropy, specific heat capacity, thermal expansion, and expansion of water. Okay. So temperature, right? A number that corresponds to the warmth or coldness of an object, right? And obviously we measure temperature with a thermometer, right? That is our measuring device for temperature, all right? And we have different temperature scales, right? I know you're accustomed to what two temperature scales? Fahrenheit, Celsius, right? And in science, we have a third one, and it's called Kelvin. And I guess we will get to that at some point, okay? So, how does temperature, where does temperature come from, right? So temperature is proportional to the average translational kinetic energy per particle in a substance. So, for instance, a gas, right? A gas has particles that are moving around in a space, right? Especially if the gas is contained in a space, or some type of container, okay? So a gas is made up of particles in the space, right? And those particles are constantly moving around, vibrating, rotating, excuse me, colliding against each other, okay? And so the difference between a gas, a liquid, and a solid, right, are how fast, right, those particles are moving, bouncing against each other, right? Obviously, in a gas, they're bouncing and moving around the most, right? You go to a liquid, right? A liquid, so a liquid, when I take something liquid and I put it inside of a container, right? Then that liquid is going to take the shape of the container, right? And obviously that's not the case for a solid, right? A solid is what it is, right? And it has a definite shape, right? And in order to change the shape of a solid, what must we do? You can break it, right? But what are we talking about though? Temperature, right? So in order to cause the particles to move faster, I have to melt. And then I get to a liquid, right? And then for my particles to move even faster, then I have to do what? To go from a liquid to a gas, I do what?
Apply heat so they evaporate.
Evaporate, right? Good. So heat, yes, heat is the catalyst for that reaction. Okay, and so thermometer measures temperature by expansion and contraction of the liquid, right? And so we are familiar with a thermometer, and it has the mercury inside of the thermometer, and yeah, and there's different types of thermometers, right? I have some different ones across the hall. right? Or different types of measurement tools, I should say, or temperature measuring tools, okay? Some of them can use infrared, right? And I think y'all got familiar with that with the COVID, right? When you walk into the place now, they take the little thing and they scan your head for your temperature, right? So that works a little different from a thermometer. Well, a thermometer, you gotta do what? Put it in your mouth, or, you know, in some type of orifice. All right? So yeah, that's a thermometer, right? And so yeah, this is what I was talking about with the temperature scales, right? Obviously, Celsius and Fahrenheit. Right, and of course, 0 degrees is freezing to 0 degrees C, right? That's the freezing point for water. 100 degrees is the boiling point, right? And of course, we can convert those two, right, from one scale to the other, right? We can figure out what the boiling point is for water and the freezing point for water in Fahrenheit, which is 32 and 212, right? But that's from a formula, and I guess we're gonna deal with that formula at some point, okay? And so I also talked about the Kelvin scale, right? This is the scale we use in science, all right? Kelvin scale. Kelvin scale goes a lot lower than Celsius, okay? So the 0 at 0 degrees Kelvin is negative 273 degrees C, right? That's an ideal. That's almost impossible, okay? Nothing in the world exists at 0 degrees Kelvin, but a lot of things exist at 0 degrees C, right? But at 0 degrees Kelvin, life would not exist because there would be no energy, right? And if we go back to what we talked about before, right, is that energy and mass are related, right? You remember that? Kinetic energy and all the stuff we talked about with momentum and all of that kind of stuff. Hopefully we remember that. All right? But the point is, 0 degrees Kelvin is very, very cold and probably does not exist in the real world. Okay? But we need a reference point in order to make sense of things. Okay? But nothing exists at 0 degrees Kelvin. Only things on the computer. All right? So, kinetic theory of matter. Matter is made up of tiny particles. That's what we've been talking about, right? Things like these little particles that's bouncing around, colliding against each other. Okay? And so, like I said, the difference between the states of matter, solid, liquids, and gases, are basically how much they are bouncing around, right? And that's determined by the bonds, right? So in a solid is bonded, right? The atoms or the particles inside of it are bonded together, right? They have a crystal structure, okay? That's why a liquid takes the shape of the container it's in. When you pour a liquid in a container, it takes on the shape. If I put a solid in the container, it doesn't change its shape. It just remains the same shape. It's because those atoms are bonded together. In order to break those bonds, I must heat them up. And when I heat it up enough and break those bonds, it goes to a liquid. That's called melting. And then when I heat it up even more and separate those bonds even more, they're weaker bonds at that point, right? There are weak bonds in liquid, right? Because if I pour a liquid here, I pour some water here, right? It's gonna spread out, but it's gonna stop at some point, right? But a gas, if I let a gas out of here, a gas is gonna do what? Go everywhere, okay? Or as far as it can go. As far as it can travel, it's going, okay? And a liquid goes solid goes nowhere until I add heat. So this is what I'm talking about with absolute zero, right? So you can see, right? So this is sort of some of the things you can get an idea of, right? This is the hydrogen bomb, right? That's what is that, 100 billion Kelvin? 100 billion. So the hydrogen bomb, right? Is that the one that they dropped over there? Got which one it was. What was it, Nagasaki or Hiroshima? One of them, okay? But that's a bomb. And look at the center of the sun. There's less heat than the bomb they dropped on them folks. Right? So the sun is not even as hot as the bomb. Okay? Right? So surface of a hot star. Right. So here we're right at the surface of the sun right here, 6,000 Kelvin. Right? And of course, you could not survive at the surface of the sun. Right? So let's see where we at. Where are we? We are probably, I think we at like 300. Where we at? Yeah, we somewhere around here, right? We somewhere around this area. Right? That's where room temperature is about what? What is it? Yeah, whatever, 70 something, 75, 70 something. So we right around there. Okay? But that just gives you an idea of the scale, right? And so down here, this is 0K. Remember I told you nothing exists at 0K, right? So helium boils at somewhere around 4K. I don't know if you have anything, if you know anything about helium, huh? Yeah, it boils.
So if you listen to oxygen have like that liquid
Yeah,
form,
how does it
Huh?
so like if it gets cold enough, oxygen turns into like a liquid.
Yes.
Huh? Like in the oxygen tank?
Yes. 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 Hydrogen too. Right? Or you can change the pressure. That's what we're talking about, right? Chapter 5. Right? Changing temperature is like changing pressure. I get the right pressure conditions, then yeah, I can cause oxygen to go from a gas to a liquid. Yes. Same way they do with what is it? Nitrogen.
Does that kind of relate to like humidity and all that stuff?
Say humidity. Well, humidity is just talking about like air, like like the water vapor in the air.
Or related to like oxygen in itself?
Well, we talking about like like a gas, like oxygen, just oxygen, pure oxygen, 99.999% oxygen, right? Or helium, like that's what they use in the rocket, in the space rocket, right? You gotta compress it. I think it's helium. It's either helium or hydrogen or something. It's one of these little light gases, okay? Gases that are like at the beginning of the periodic table, okay? And so, you gotta either compress them or, like I said, get the right kind of conditions set, and you can change a gas to a liquid. Yeah, it's done all the time.
But it's hot, wait, you say liquid hydrogen. For rocket.
That's what I just said, liquid hydrogen. I
You
said
said
hydrogen.
liquid, sure, so I looked it up.
Okay, liquid hydrogen, helium, one of them. I said all of those little small elements. the small elements at the front of at the beginning of the periodic table, right? So yes, so liquid hydrogen. But good, I'm glad you looked it up. I'm glad you had that presence of mind to use your cell phone, okay? All right, so again, absolute zero is the lowest limit of temperature at negative 273. Atoms or molecules have lost all of their kinetic energy, right? So, when you have lost all of your kinetic energy, what do they call that? Start with a D. Death.
Oh.
You are done. When you have lost all of your kinetic energy, you are done. Okay? So that's why I say 0 Kelvin does not exist. Not in this world, because we have life in this world. And in order to have life, you must have energy. All right, so here, I guess this is what we were, let me see, as temperature of a gas changes, it's kind of, this is kind of what we were talking about, right? But here, right, this kind of looks like well, it's just a container, it's not really a piston. But if you look here, right, is at 0 degrees, the pressure is constant, right? Volume changes by 273rd for each degree Celsius. At absolute zero, lowest limit of temperature, molecules have lost all volume, right? So, so essentially, right, I can compress, right? Like I said, like I was telling you, I can compress molecules, right? And when I compress them, right, I can get the energy out of them, right? So that's essentially what we're doing here, okay? So, thermal energy in the sparkler, okay? Temperature of sparks very high, all right, a lot of energy per molecule spark, all right. Total energy is small due to relatively, yeah, I don't know what, wow. I mean, a sparkler, okay. Thermal energy in the sparkler. So heat, what is heat, right? Heat is defined as a flow of thermal energy, right? So heat is a flow of thermal energy. Natural direction of heat flow is from higher temperature to lower temperature, right? So heat always flows from hot to cold. The only way heat flows from cold to hot is that you have to input energy, meaning you have to force whatever it is, right? If it's an engine or something, right? They got engines that work that way, right? They work on differences in temperature, right? Create two reservoirs of a substance, and the differences in temperature can, like I say, produce some energy, right? Which the engine is made to exploit, right? But the point here is that heat flows from hot to cold, always, right? And never the other way. All right? So now I guess we're getting into heat capacity, right? So 1 liter of water in the left pot, 3 liters of water in the right pot. Both pots absorb the same quantity of heat. Temperature increases 3 times as much in the pot with a smaller amount of water, right? So the heat can be the same, but the temperature, right? You finished?
Yes, sir.
All right.
Go with ratio.
Yeah. Are you gonna write your name on this one too? Where's the other portions? Yeah, so here heat, right, temperature and heat are two different things, right? Temperature and heat are two different things, right? Heat is the flow of energy, all right? So quantity is, quantity of heat. Heat is energy in transit, right? So like I was saying, right? Heat is the flow of energy, okay? That's what heat is. And of course, we have a unit, right? Whenever we introduce a new quantity, we have a new unit, and that unit is a calorie, right? And so a calorie is defined as the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius, right? And so that's why it's, right, when you're doing exercise and things like that, right, you're measuring the amount of heat, right, the amount of heat that your body is generating, right, and that's how they're able to calculate calories burned or whatever it is on the treadmill or whatever it is you do at the gym. All right? And so, obviously, we get energy from food. So food has a certain amount of calories in it, right? That's why we can, based on whatever we eat, we know that's how much energy we will have, or you know how that works, right? We don't eat, we don't have any energy, and so on and so forth, right? But energy rating of food or fuel measured by energy release when they are metabolized, right? Blah, blah, blah. All right. So, heat is energy in transit. So I guess, yeah, this is just a summary, right? So heat is energy in transit, right? It's just the movement of heat, or movement of energy, right? So in order to create heat, I need a difference in temperatures, right? Or to create heat flow. Well, heat, right? Heat is flow, right? Heat is flow. So I need a difference in temperatures to create a heat flow. All right? And so the laws of, and so obviously that leads us into a discussion about the movement of heat, which is thermodynamics. That's what I was telling you earlier, right? And everybody in here is familiar with certain laws of thermodynamics, right? And the one we all are familiar with, or we should all be familiar with, is what? Energy can never be created or destroyed. Good, everybody's heard of that, right? That's a certain law of thermodynamics, right? That energy is never created nor destroyed, right? That's why we was talking about the heat, right? That once you lose it, right? So when you're sitting at the light, idle in your car, in your gas burning car, right? That gas is being burned, producing a bunch of energy. That energy is being used to move your car around as well as generate heat. And when it generates that heat, it loses it, right? Or I shouldn't say it loses it, but it gets, well, it moves to somewhere else, right? That energy goes somewhere, is my point, okay? It's never created nor destroyed. So all of the energy that's here now will always be. And that's what we were just saying. This is the second law of thermodynamics, that things flow from hot to cold and not the other way around, right? That's the second law of thermodynamics, all right?
How does like a microwave work?
Well, a microwave, I think is, I think that's like microwaves, energy, right? Like, I don't know if you understand, like electromagnetic energy, electromagnetic waves, right? It's on electromagnetic spectrum. So a microwave is just a certain type of energy. It has a wavelength, right? And I think what happens is those waves just transfer. So what they do is those waves get absorbed into whatever has water in your microwave. So that's why you should never put metal in your microwave, because metals don't have water. So what happens when the microwave hits a piece of metal? Well, eventually it's going to say boom, yes, but it hits the metal and it gets reflected.
Bounces off.
It keeps bouncing off, right?
Yeah. Makes sense.
Okay.
Oh, it's gonna start.
So, second law of thermodynamics is heat never flows from hot to cold. Cold to hot, only hot to cold. All right. And the third law is what we just talked about, right? Is that what? No system can reach absolute zero because it's too cold, and life cannot exist there. All right. So now we talk about entropy. Entropy is a measure of the disorder of a system. Right? It's a measure of a disorder of a system. Okay? So entropy is, or how I like to remember, or how I like to conceptualize entropy in my head, right, is if I clean up my room today and I come back a week later, will it be cleaner or dirtier? Dirtier. Why?
Cause you're not continuing.
You're not
Yeah,
really
you clean it every single day.
And right, so the universe tends to go towards what?
Disorder.
Disorder. Right? My room will never get cleaner. It will just never spontaneously get clean. Right? It's going to always get more and more disordered. Okay? So that's how I like to remember entropy. I mean, it's a little bit more complicated than that, but that's a good way to start. Okay? So natural systems tend to disperse from concentrated and organized energy states towards diffuse and disorganized states, right? That's what the universe tends to do, right? And there are certain instances where the universe will spontaneously order things, but in most cases, the case is the universe prefers disorder. Okay? And the total amount of entropy in any system tends to increase with time, right? That's basically what we're saying with your room will never get cleaner over time. It will always get dirtier. Okay? All right. That's entropy. That's good enough. Okay? and specific heat capacity. Excuse me. So heat capacity is exactly what it is. How much heat can a object or substance hold, right? And so it's defined as the quantity of heat required to change the temperature of one unit mass of a substance by 1 degree, right? And so water is one of those substances that has a pretty good heat capacity, right? Why it takes you a little bit of time to get water to boil, right? Because water absorbs a lot of energy. Well, I guess that's a good. Water refilling has more capacity for storing heat than pie crust, so I guess that's why when you eat the pie, the filling in the inside is a little bit hotter than the crust, right? Because it has more water in it, and water absorbs heat, okay? Specific heat capacity, all right? And so, obviously, right, that's how we get a lot of our different changes in weather patterns, right? From these huge bodies of water, right? We get all kind of hurricanes and all kind of stuff like that, right? We get all of that because, right? Because what? Because particularly in this part, right? Because this is where our hurricanes normally coming from, right? Off the coast of Africa. Y'all knew that? Okay. That's where hurricanes come from, Africa. Okay? Now y'all can think about why they come from Africa. I'll let y'all figure that out. But that's where they come from, Africa. Huh? You said something? You say what?
Cause hot.
Well, that's one of the reasons, right? Because of the water, right, absorbs so much heat, right? That's why the hurricanes tend to come during the summer or towards the end of the summer, right? August and all of that, right? Because more heat is absorbed in the water. And so it's the heat in the water that is driving the hurricane. That's why, that's why we get, the climate is changing more and more, right? They say we're getting hotter and hotter. We get hotter summers and hotter summers. We get what? Worse hurricanes. That's why you see Katrina and blah, blah, blah. And technically they should get worse, I guess, if we get hotter and hotter, right? But that's what's driving hurricanes, right? The heat that's being absorbed in the water, in the ocean. All right, now thermal expansion, right? Now due to the rising temperature of a substance, molecules jiggle faster like we've been talking about, and they move farther apart, okay? And so we all know heat expansion. We all know that if you heat something up, eventually it's gonna, you can pull it apart easily, right, when you heat it up. Okay? So that's what heat expansion is. And obviously, right, that's why when you go on the interstate, right, every so often on the interstate, you're gonna have a piece of metal, right? Does anybody know why? Right? Because if the entire interstate or the entire highway was made of concrete, then when the sun beat down on concrete all day long, what happens? It's going to eventually crack it because the sun is causing that concrete to do what? Expand. And then when the sun goes away, what does the concrete do? Contract. So if I expand, contract every day, eventually I'm going to do what? Crack. Anything. If I expand something and contract it every day, whatever that thing is, it's gonna fail one day. That's the nature of our work. It's called degradation, right? Nothing lasts forever, right? So a good example, right? And that's what I was just talking about, right? The highway. So that's what you see on the highway, right? That little piece of metal right there. So that's to account for what? Expansion and contraction. That way the interstate won't form all of these cracks in it.
I thought that was so that how it didn't flood.
How it didn't flood?
Yeah.
Okay. Yeah. No, that's for expansion and contraction, right? And you'll see, right? And sometimes you'll see the buckling in the train tracks, right? And that's because, you know, train tracks are metal, right? And so they don't necessarily crack, but they do what? Bend. Metals don't crack, right? Unless you make them extremely cold and then crack them, right? But metals don't crack, they bend. That's why an airplane is made of metal. So in case it crashes, and, right, there's at least 2% chance you'll survive. All right. Expansion of metal. So then we gotta finish up right quick. So this is how your air conditioner works, right? Your air conditioner has a thermostat in it. A thermostat. That's how it works, right? It's you set your thermostat to a certain temperature. You say, hey, I want my air conditioner to come on when it gets 72 degrees in my house. Okay? And so based on whatever temperature you set, right? There's a piece of metal or a piece or a metal that's contained of two different materials, but they are connected together. It's called a bimetallic strip. Okay? And based on the temperature between the inside of your house and the outside, those two strips, they bend, right? And so when the temperature between the outside and the inside of your house gets too much, that strip bends and it forms a complete circuit and cuts your air conditioner on. So your air conditioner, the thermostat in your air conditioner works by thermal expansion.
So the older ones that show you like the little red thing that be moving back and forth, is that what also makes that move?
The old ones that show you the red thing, which ones?
Like some, yeah, like, and like my brother's house. there's like
Yeah, I know what you're talking about.
Okay.
Well, I mean, that's just the gauge though. I'm talking about the actual, yeah.
Like when it bends, it makes that move. Like, you know, like our gas tank, like if it's full, it like go up. You know what I mean?
Oh, no. That's just telling you what temperature it's at, right? That's just telling you what temperature it is in the house, right? Is it?
Mm-hmm.
That's what, when you talking about that little thing you turn, one of the mold things, and they got the little red thing, yeah.
Mm-hmm.
That's just telling you, or allowing you to set the temperature at what you want it to be in the house.
Okay.
So what it does is, once you set that, it compares that to the temperature outside.
Mm-hmm.
Right? And based on the difference between those temperatures, right, that metal, right, see here is brass and iron, two metals, a bimetallic strip, right, it bends based on the difference between the temperature inside of your house and outside. And so at some point it bends and it connects and forms a complete circuit to cut your air conditioner on, right? That's how your air conditioner is able to, or your central heating is able to work. Okay? All right. Thermostat, that's just what we was talking about, blah, blah, blah. And expansion of water, right? And so water is, and I'm gonna wrap it up here, water is very unique in the fact that what? When water is cooled, right, it expands. Everything else does what? We just said it.
Like comes dense.
Contracts.
Sure.
But water, when it's cooled, it expands. That's why ice does what?
Float.
Floats on water. It's the same substance. Ice and water are both water, right? But ice is the solid form of water. So it should be more dense than the liquid form. So why does ice float on water?
It's the hydrogen bonds and all that, huh?
Hydrogen bonds, right? Water is a very godlike substance, right? It's very powerful, very unique, right? Very different from almost anything in the universe, okay? I don't know if you've ever heard, right, that there's nothing more powerful than water. Nothing, right? If you drop water on something continuously, it will eat through it over time. You might not see it, it might not happen in your lifetime, but water will go through anything. All right? So, water is like a very peculiar substance that way. Okay? But that's the lesson, that water, when it's cooled, is less dense. That's why ice floats on water. And that's why the fish in the sea are able to live. Because what would happen if the glaciers didn't float? They would sink, and then they would do what? Crush all of the fish. All right, we're going to skip all that. We're going to do some more stuff. All right, y'all. That's it. Yeah. Nah, no roll.